All right, so our next speaker is a principal scientist at Science Laboratories, was a postdoc with Claudio Orlandi, a student of Abi Shalat, and has done a bunch of influential work on threshold ECDSA. So very looking forward to the talk.
Yeah, thanks for that really nice introduction. So this is joint work with Nidish Bemrajka, Daniel Noble, and Supreet Varadarajan. Okay, so I'll begin with a quick introduction to the account aggregator ecosystem, which is an open finance framework in India that's regulator driven. I will talk about some gaps that we've identified in this context in terms of trust and incentives. So we will show that we can use MPC as a way to mitigate some of these gaps, to mitigate some of these problems. In particular, we're going to address concerns of data duplication and come up with a more fair compensation model for all the actors in the ecosystem. And I'll also discuss our main design principle in constructing these protocols, in particular that of designing a drop-in replacement to decentralize entities that already exist as part of the existing protocol. And I'll talk about why this has been difficult for us technically. Okay, so this is a quick refresher. Secure multi-party computation at MPC considers a setting in which a number of parties have some private inputs and they wish to evaluate some function on their joint inputs. So ideally, they should be able to do this by sending their inputs to some trusted oracle that is able to compute the output without revealing any intermediate state. But of course, such oracles don't exist in the real world. And so MPC protocols let us achieve this effect in a secure manner. So that out of the way, let's talk about open finance. And so open finance at a high level consists of frameworks that enable people to securely mobilize their personal financial data in order to avail of some services of some financial nature. So think about scenarios in which you have to prove your financial health to some third party. For example, if you're applying for a loan or if you're applying for an apartment or something like this. So in a lot of scenarios, this can take physical unverifiable forms, or like other sort of heuristics could be used. Think of using like physical documents to certify your bank statement or something like this, or also think of other even worse things where you have to hand over your banking credentials to some third party that then logs in on your behalf and does some screen scraping or something. So open finance frameworks basically replace these kinds of heuristics with rigorous cryptographic protocols. So the account aggregator ecosystem in India is one such framework, and that's going to be the focus of this talk. It is regulated, albeit indirectly, by the central bank in India. So in this framework, users are able to consolidate their financial information across multiple regulated FIPs or financial information providers. Think of these as banks and so on. And upon the user providing consent, the AA shares a curated view of the user's finances to licensed third parties, licensed financial information users or FIUs. Think of this as maybe insurance underwriters or loan granting authorities and so on. So according to Sahamati, which is which handles governance in the AA ecosystem, the ecosystem as of last year had over 80 million users, over 100 FIPs, and over 400 or so FIUs. But there are still some issues that pose some barriers to scalability of the system, which I will discuss. So these are the actors involved at a high level: the financial information providers, information users, and the data principal or the users of the system. And the account aggregator is an entity that sits in between all of these and coordinates them. So the first step in the workflow for the account aggregator system is for the user to consent to its data being shared. And upon receiving a request along with the public key from the FIU, the account aggregator forwards these things to the FIP, which then retrieves the relevant data, encrypts it, and then forwards it through the account aggregator to the FIU. And on receiving this ciphertext, the FIU decrypts this data and processes it as required. So if we zoom out for a second and see who puts in what and gets out what, we see that the user provides consent to move its data from the FIP to the FIU through the account aggregator, which basically acts as a pipeline that maps consent to data being available. And the FIU is compensated by whatever business model it has. The account aggregator is explicitly compensated through fees from the FIU, and the user presumably had some reason to initiate this process to begin with. And already we start to see a gap in incentives, and that the FIP gets nothing out of the system, at least the way that it stands. But perhaps a more pressing concern is the fact that the FIU gets to see the plaintext data of the user. And this can be a problem, especially if the FIU were to be compromised at some point, right? In more detail, if imagine a scenario where there's a data breach or an insider attack or an FIU, or even just a rogue entity operating the FIU, this could result in the data ending up in the wrong hands. So this directly affects users because they lose control over their personal financial information. And also in a larger scale or at a macro level, FIPs are also affected because user data is considered their proprietary data. And having it lost can cause many problems reputationally and also for their business. So this issue has already been identified, and to our knowledge, there are already heuristic solutions that FIPs use to address this problem. Specifically, one that we know of is that they throttle the response rate. That is, they respond only to a fraction of the requests that they get. And on the one hand, this undermines faith in the ecosystem because now this compromises liveness. And on the other hand, this is still a bad solution because data is still leaked. Like there's no rigorous guarantee of privacy or anything. So what we propose is using a more compliance by design approach in this framework. Let me say a bit more about that. So this is our workflow back up on the slide. Let's zoom in on what the single point failure is. It's clearly the FIU endpoint. So our proposal is to replace this single point of failure endpoint of the FIU with a decentralized system that is a network of financial information compute units, each of which are operated by entities that are carefully chosen. And the idea is to have the FIU's role be fully decentralized. So these FICUs get together and jointly emulate a single FIU. So who actually operates these nodes? Right? The idea is to pick operators who are naturally incentivized not to collude, such as the FIU itself, the FIP, or a proxy that represents the interests of the FIP, and also the infrastructure provider who's interested in maintaining the credibility of the ecosystem. So this gives us a solution that addresses both these things at once. It addresses duplication. It addresses concerns of data duplication, because now the only way you can access the data is through this MPC. And at the same time, this also allows us to come up with some sort of compensation model for the FIPs, because we can track how frequently data is used and what is used for and so on. And this gives some way of valuing the services that the FIP provides, which is a general problem. Okay, so in a little more detail, what we're proposing on a technical level is an MPC in which there are 3 parties, and we assume up to 1 active corruption. So we're in the malicious security setting. And the ideal functionality that they have to realize is as follows. First, they create a public key and secret key pair. These little box brackets indicate secret shared values. Then through the AA ecosystem, they're able to get a ciphertext that encrypts this relevant data. And then they decrypt the data and operate on it as per their business logic. So the last step, that's operating on the data, is something that can be studied as an independent MPC problem and is not going to be the focus of this talk. What I'd like to focus more on is how the retrieval of data from the ecosystem works. So roughly, this corresponds to this problem of threshold decryption, which is a well-studied problem in the MPC literature. So as a simple baseline solution, you can think of the encryption algorithm being, what if we could tweak the encryption algorithm so that it just directly encrypts secret shares instead of something more that needs a more involved MPC. Right? And therein lies the problem, in that the moment we start thinking about how do we tweak the standards, we run into issues with real-world adoptability. So there's this old cartoon and this old saying on the internet that on the internet, nobody knows you're a dog, which I interpret roughly as being that as long as you follow the protocols as prescribed on the internet and you provide a standard interface and so on, like nobody actually cares what you're doing behind the screen. And like extending this logic a bit, like in the same way, if we're using an MPC to decentralize one of the endpoints, let's say, the rest of the ecosystem doesn't really care that we're doing this. All they care about is that we conform to the standards that apply to everyone, right? And that we're compliant with whatever protocols there are. So this informs our design principle, which is that we acknowledge that the protocol specifications for the ecosystem are set independently of MPC, and we aren't going to sit around advocating that the entire ecosystem change to be more MPC friendly in some sense, right? So we design a solution to be a drop-in replacement for the FIU role as it exists today, so that we can integrate with the AA ecosystem right away. So this is all well and good, but this does cause some problems for us at a technical level. That is, from an MPC protocol design point of view, we encounter these challenges. The first challenge is that now decryption is now a non-trivial function to handle within MPC. The next challenge is that after we've decrypted, even assuming that we've decrypted the data, the result of decryption is an XML file, right? And we now have to parse this XML file into a format that we can actually operate on inside of the MPC. So let me give a quick overview of how this works. So decryption involves 2 steps. The first step is some sort of key encapsulation that's pretty standard. And then the next step is to use this sort of derived shared key to key AES, to evaluate AES. So the first step of the key encapsulation, which is a public key operation, is best represented through the standard elliptic group operations. And the next stage of key derivation is to like hash the resulting thing, which is best represented as a Boolean circuit. And luckily, it turns out that there's prior work on like oblivious TLS and so on that we can borrow some ideas from. And at a high level, what we are able to do, so what we do is we are able to convert these elliptic curve shared values, I mean, value shared in the elliptic curve group to value shared in ZP as arithmetic shares, where this corresponds to the base field of the elliptic curve. And then we convert these arithmetic shares to Boolean shares using standard techniques. And then we're able to evaluate these Boolean secret shared values in MPC. Once we have secret shares of the key, we can then evaluate AES securely inside of an MPC. And now the question arises as to how do we do this, or like what's the most efficient way to evaluate AES in this context? Right? So conventional wisdom suggests that using a low latency approach, using an approach that optimizes round complexity usually wins out. That is, if we use garbled circuits which have, which permit constant round protocols at the expense of a lot of communication, this does suit a lot of settings. But interestingly, in this setting, given that AES is used in GCM mode, all the AES invocations are done in parallel. And so the decryption function for the circuit that corresponds to decryption over here is a very parallel, like a very wide circuit. So as the ciphertext grows in size, the decryption circuit effectively grows in width and not in depth. And what that means is we notice that rather quickly that for ciphertexts that are just the order of kilobytes or larger than that, the so-called secret sharing based approach, where the rounds of the computation scale with the depth of the circuit, like this wins out pretty quickly. So we opt for a more secret sharing based approach in our thing. So like think of these BJW, GMW type protocols. Right, so that's decryption handled. Now what about the next stage, which is parsing the data after it's decrypted? So to see why this is challenging, let's consider like a naive way of solving this problem, right? So the plain text that we get after decryption, or other secret shares of this plain text that we get, consist of a list of transactions that are formatted as shown on the slide. So think about how you would parse this value in plain text, right? The first step would be to identify where the delimiters are. The next step would be to read, between the delimiters to like cast this into whatever structure you want and then use it however you desire. So what if we were to do the same thing in secret shared form? Right, so the first step would be to identify where the delimiters are. We expose the locations of these delimiters. And it turns out that doing this already has an unacceptable level of leakage. Specifically because the length of each field is variable and the length of the field depends on the payload that it carries. This causes some significant issues. For example, the second field over here corresponds to the amount value of the transaction. And just the number of characters required to represent it leaks the order of magnitude of the transaction amount. And so we can't do something as naive as just exposing delimiters and working from there. So the ideal situation would be if each entry were to be padded to some maximum length value so that it's safe to expose delimiters at the very least. To make this a bit more concrete, in this scenario, this would look something like this, where there's some public max row length parameter, and every field consists of some actual payload and some number of padding characters that make the difference between the payload and the maximum length. And so if we had a situation like this, it would be ideal because it would make parsing very simple. And our approach roughly is to construct an MPC protocol that effectively derives a string of this format, or a secret shared string of this format. The protocol is a bit involved, so I'm not going to get into the details so much, but I would like to convey a flavor of how this works. So we begin with the secret shared string, and then we compute using some comparisons the locations of all the delimiters, and that for every index, we check if the corresponding secret shared character is a delimiter or not. Using this, we can then compute a relative index value, which is what is the distance between any given character and the last delimiter that was encountered in parsing the string. And with the relative index in hand, we can compute an absolute index. That is, if we were to complete the padding process, what would the index of every given character be? Right? So this is also an easy computation. And after this, we do a similar but complementary thing, which is we start with a public padding array. And using a secure protocol, we figure out which indices of these pads are actually required. So we get the absolute index of the required pad values. And the effect of this is now we have two arrays, right? One array that consists of the locations of the actual payload values, and another array that consists of the locations of the padding values, post padding. So all that remains to be done once we have these arrays is to securely merge them, because these are basically two perfectly complementary arrays in terms of indices at least. Yeah, so that's how a secure parsing protocol works. So like this is roughly how a padding and then parsing routine is structured. So this is not terribly inefficient in that it costs a constant number of operations per character, so constant number of additions, comparisons, and share conversions, like the latter being the most expensive, and also needs some small number of shuffles, for which we use a simple custom protocol. And what we achieve is a protocol that has an overall run complexity that's independent of the size of the file that's being parsed, which is useful. But still, at the end, this ends up being the most expensive component of the gadget that integrates our MPC with the account aggregator ecosystem. So while this is the most expensive part, it takes, I think, from what we found, on the order of a few minutes, a few minutes to process a relatively small encrypted bank statement, but nonetheless an encrypted file that's obtained from the actual account aggregator API as it exists today. There is, of course, plenty of scope to improve the protocol design and also to tighten our implementation and so on, but we do already have a pilot deployment in the works with multiple partners, including an FIU, a technology service provider, and also a service provided by Samati, which is the regulator for the ecosystem. Right, so to conclude, open finance frameworks are increasingly used worldwide, with India's account aggregator framework being one such example. And we show that certain gaps in these frameworks can be plugged using an MPC-based solution. So this is not a problem that's unique to the account aggregator ecosystem. This is really a concept that can be generalized to different jurisdictions and so on, under more general terms such as data fiduciaries instead of FIUs, data custodians instead of FIPs, and so on. And the main design principle behind our solution is to really prioritize it being a drop-in replacement to operate within the ecosystem as it exists today, rather than trying to advocate for MPC-friendly standards and so on. And pretty soon, we will have our full protocol specifications and so on online, along with a report on our pilot deployment and so on. And if you're interested in the meantime, we are consolidating some resources at this link on our website. Thanks for your attention.
Hi, so this bank statement is about a few kilobytes, yeah? And then you decrypt it in MPC, you do the ECIS and decryption, and then you've got this really cool parsing protocol, which I really liked. And you said the whole thing, I think on the previous slide, took a couple of minutes or something. Is that right?
Yeah.
A couple of minutes. So what percentage of that is the ECIS bit?
So what percentage of that is the?
It is the elliptic curve and then the threshold GCM. Is that the majority of the effort?
No, it's a small minority, like in the order of minutes, like that's on the order of seconds.
So most of it is the parsing bit.
Yeah.
Oh,
exactly.
okay.
So maybe this last question.
For the parsing, the format is XML, right? Why not just require the data source to pad it with spaces so that it lines up nicely?
Yeah, I mean, if people are willing to change things in the ecosystem for us, we could do that. And ideally, once this system gains some traction, maybe we can advocate for it. But at least the principle that we have now is that we want to work with data exactly as it comes. And it's at the moment done by banks and so on that are not very willing to change what they do.
Great. So let's thank the speaker again.